Hello everyone. A new learning algorithm is introduced today called the forward-over algorithm for neural networks. This algorithm replaces the traditional back propagation forward and backward channels with two forward channels, one for positive data and the other for negative data. Each layer has its own objective function and has a positive effect on positive samples and a negative effect on negative samples. The sum of the square of the activities in the layer can be used as a good or bad measure. Negative transfer can be done offline, which makes learning easier. We all know that the training of neural networks is divided into two major steps: forward propagation and backward propagation. The process of forward propagation is a kind of inferential calculation process. Given an input data starting from the first layer of the neural network and calculating backward to the last layer, output the result. The process of backpropagation is to calculate the error between the result of each forward propagation and the result that is the real result during the training of the neural network, and to calculate the updating of weights or parameters of some layers in the reverse direction, so that the next forward propagation can have better results than the previous one, round by round, until the whole network converges and the neural network finish training. Like the left image, we input the X and train it by each layers and get the result Y. This is the forward propagation, and for the backward propagation is to calculate the error between the result of each forward propagation and get the lost layer. Most of the amazing success of deep learning over the past few years also have been built on training with massive datasets and using backpropagation. This approach has worked, at least for many of the deep learning fields that have been performed, although its active brain neuroscientists have been skeptical and even opposite to backpropagation, because current scientific research hardly found evidence of the process similar to backpropagation in neurons in the human cerebral cortex. When performing memory extraction or memory storage, in other words, backpropagation, although effective, may be a different path from that of the human brain. Think about it. If AI wants to achieve true intelligence, it should at least be designed at the top level to be presumably consistent with the mechanism of the human brain. This is also makes clear that backpropagation algorithms are unimaginable as a way of learning artificial intelligence. And there is a serious limitation of the backpropagation algorithm that we need to fully understand the algorithm in forward propagation in order to calculate the derivatives in backpropagation. If we insert the black box in the forward propagation but do not know the specific algorithm implemented in the black box, it is impossible to complete the training of the neural network unless we can learn the model of the black box. As a model of all the cerebral cortex neurons, backpropagation remains unreliable because of the lack of evidence that the brain explicitly propagates error derivatives or stores neural activity for backpropagation. Furthermore, top-down connections in the brain do not reflect bottom-up connections, and backpropagation through time is unreliable as a way to learn sequence. The brain needs to process input in real time without stopping for backpropagation. We have an example in the left. You can see that we input data into the algorithm and we know the specific algorithm result, so we can do the neural network and training get the result. But if we didn't know the specific algorithm in the black box, so we don't have idea to training the model and get the result. It uses forward propagation instead of the forward back propagation. Those two forward propagation are computationally identical, but use different data sets and different final targets. In this case, the forward channel operates on the real data and adjusts the weights to increase the goodness of each hidden layer, and the back channel adjusts the negative data weights to decrease the goodness of each hidden layer. Those two forward propagation are used to calculate the adjustment of the weights for each layer. This is different from the previous backpropagation that passes the error from the last layer forward. Instead of passing the error from the last layer to update the weights of each layer, but each layer adjusts the weights by itself using the calculation of positive and negative symbols. Assuming that the company's function of the layer is the same of square of rectified linear neural activity in the layer. The learning objective is to make its goodness well above some threshold of real data and well below the threshold of negative data. The probability of the input vector being positive when it is correctly classified as positive or negative data can be determined. The logical function minus some threshold, where Yg is the activity of the hidden unit G before their normalization. The negative data may be predicted by the neural net using top-down connection, or it may be supplied externally. The mathematical formula is the probability the positive data includes the logical function included the sum of the square of the Yg minus the threshold. This section is designed to simulate the inhibition mechanism of neurons in a neural network, where the activation function is not inhibiting positive data and inhibiting negative data. The value without inhibition is high, and the value with inhibition is 2, so that the hidden layer can be learned. However, if the activation of the first hidden layer is subsequently used input to the second hidden layer, it is not important to use only the length of the activation vector of the first hidden layer to distinguish between positive and negative data. To keep the activation information of the first hidden layer from being passed to the second layer, the length of the first layer after activation is normalized, so that the second layer does not know whether the first layer is suppressed or not, and can be relatively independent trained. Backpropagation requires complete knowledge of the requirements for forward computation and its inability to handle nonlinear problems. No reinforcement learning is suggested as an alternative method and is still fully for large networks. The FFA is used as an alternative method similar to backpropagation but slower. It can be used in the paralysis of unknown exact details about the forward computation, and learns while running sequential data through a neural network without doing manual activities. For propagating arrow derivatives, the algorithm may outperform the backpropagation method for learning in the cerebral cortex and low-power analog hardware applications. Thank you for your listening.